Hello, my name is Wojtek, and for the past 15 years I have been working professionally as an engine and 3D graphics programmer, mostly in the video games industry. I worked for companies like Nvidia, id Software or CD Projekt Red. I have broad experience in creating 3D engines and in particular in programming 3D graphics. In those areas, and many others, math plays a crucial role and is one of those elements that separates mediocre engineers from the best ones. I would not have ended up in any of the aforementioned companies if I didn't have a solid math background. This course is split into three parts: analytic geometry, linear algebra, and calculus. The course puts strong emphasis on practice, but we do not shy away from theory and formulas and equations so that we may properly understand the math background behind the presented concepts. Example programs, and there is around 100 of them, are written in Unity 3D due to its prevalence and ease of use. However, the vast majority of presented information is completely engine agnostic and will apply to any kind of 3D programming. The example programs are compact, rarely exceeding a few dozen lines of code, as each one focuses on demonstrating a single concept in isolation, so that they are easier to follow and digest. The first part of the course is about analytic geometry. This is the absolute foundation that anyone needs to have in order to do any meaningful work in 3 dimensions. We cover here trigonometry in both 2D and 3D, vectors, and analytical formulas that describe geometrical objects. All the fundamental stuff. An outlier here are complex numbers, which have very limited use in 3D and games programming, if any, but we need them to properly understand certain concepts in later chapters. They are also a good exercise in trigonometry. This part of the course is available for free when you subscribe on my homepage. The second part of the course focuses on solid, practical linear algebra. We start in chapter 5 with generic discussions on matrices and transformations. Then in chapter 6 we go into specialized topics that are bread and butter of any 3D engine transformations and scene management, so things like local to world matrices and camera transformations, to name a few. We conclude this part of the course with quaternions and demonstrate their superiority over other methods of representing rotations. And spoiler alert here, it is not about gimbal lock. Finally, in the last part of the course, we talk about calculus. Here we learn what derivatives and integrals are. With derivatives, we mainly do two things. First, we solve various kinds of optimization problems, for example the inverse kinematics problem. We even learn about derivatives' crucial and fundamental role in the neural networks. And second, we use derivatives to generate tangent vectors and tangent space, and by extension how to generate normal vectors on non-trivial surfaces. When it comes to integrals, we use them in a physics context by integrating motion equations to achieve smooth camera movement under specified constraints, and also in a graphics context by calculating ambient occlusion effect. We utilize both numerical and analytical integration. If what you care about is creating games or 3D software mindlessly, using random pre-made components and assembling an unstable troll out of them, then this course is not for you. However, if you want to know the backbone on which real 3D technologies are crafted, then you really want to go for this course, to which I am sincerely inviting you.